the undergrad topics. Undergraduate topics, we have tapered line, no one chose that yet. Wilson power divider. That is chosen. Quadrature hybrid. Looks like we have people for that. Line coupler is not chosen. An 8-degree hybrids is chosen. No, wait a minute. No, that's not chosen. Step impedance, two candidates for that. We need one of them to choose something else. Coupled line filters. That is chosen. Infrared circulators. Infrared isolators. These were not chosen. Thank you. That's a baby one.
The only one I could find inside the others.
Okay. That's a baby magnetron. I can lift it with a couple of fingers. Well, thank you, Sean. Multi-hole directional coupler. These are undergrad socks. Coupled line couplers. Filter designed by image parameter. All these have not been chosen yet. Filter designed by insertion loss. Filter transformation. That is chosen or was decided. Filter implementation. That's not chosen, and then coupled resonator filters. This was the one that everyone wanted. Since we allow two people to work on the same topic in the undergraduate side, then I would say I already have two candidates here. I already have two candidates here. And I have one candidate for topic B, which is the coupled line coupler. One person. All right,
if I go with first come first serve, let me tell you who got what, right? So the two E's are Pierman and Fan. These are the two E's. The two G's are Smith and Shamuddin. And the 1B is Gallagher. Okay. Following the same rule, Zhang got this one. Himstra got this one. Mao got this one. Cunningham got what? Step continuous. Yes, Cunningham here. And small screen here. Apologies, like I said, Gartland got with the right circular. Let me see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 5. And this one here, I didn't get the other set. So why don't we try to finish that now if we can? Does this seem to be okay? Any observation here? Sean asking for something outside the scope of all this. I'm waiting to see if everything else is covered. Then you can get what you want. I just want to make sure that we cover those first. Did I do any mistakes here? Okay. Who's not here and wants to take what? You asked for G as well. You asked for
Oh, yeah, but I didn't.
where? This one, right? You and Matt both asked for this. I had 4 people, but already 2 ahead of you. So if you want to go for anything else, if you want to go on the right-hand side, that would be fine too. Who got this one here? Couple line filters. Is that taken as well? No, that has not been taken. That was a mistake here. So, this is close. You want to get that?
Oh, I'm sorry.
Yes.
I'm fine with like picking something else. Like,
All right.
It's not a big deal.
No, I was offering you this topic here, which is close to this one. right?
Okay.
Which is couple line filters, that's couple resonator filters, so. All right. You think Matt will go for that as well?
Yeah.
All right. Looks like you guys work together, so. All right.
Can I do the line coupler?
Line coupler. What was your other choice?
I don't think I had.
Hmm?
I don't think my name was on there.
Oh, you name, okay. So how do you spell
Klein, K-L-E,
K,
L-E,
L, E?
I-N-E.
I'm not good at spelling. Line, right,
And-
okay.
An extra E, that's fine.
Yeah.
Another E.
I'll do the one under it, the hybrid.
You want 1.8 hybrid?
Yeah,
All right.
thank you.
So I'm taking this to this side.
Okay.
You're ready, right? Yeah, so you're fine. So I'm gonna take this here, to this side here. Have a different
Oh,
way to spell.
sorry, I didn't
That's fine.
realize the,
That's fine.
Okay.
You know, if no one else is taking, unless I have any of the other guys wanna take this. Give me
gone.
your spelling.
Oh, yeah, I-N-G-V-O-L-D
I-N-G-V-O-L-D
D
D.
S-T-A-D.
S-T-A-D. All right. Well, since I allow two people to work on the same topic, if a grad student still wants that, that's fine too. Who else is missing?
What's that topic about? Is it filter implementation? The
Which
second
one?
of that?
Filter implementation?
Yeah, I'll take that one.
You'll take that?
Oh, Chef.
Huh?
Chef.
Yeah, I know, but you know, how do you spell it?
S-H-E-T-H.
S-H-E-T-H. All right. When I see it, I can read it, but it doesn't work backwards sometimes for me. Huh?
Actually, all the good topics that you can take it again.
You want to take anything here?
Yeah.
How about the tapered lines or the 180 hybrid?
So you cannot take the
Hmm?
you cannot take the Wilkinson power divider with the latch coupler or the couple line filter again.
Well, these are already presentations that are made, so we don't want two presentations on the same topic.
Okay, I'll take the 180 degree hybrid.
Hmm?
I'll take the 180 degree hybrid.
Can't hear you.
I'll take the 180 degree hybrid.
You want it to get hybrid. Give me that spelling.
ADS,
A,
D,
A, D,
yeah, I,
I,
TH,
can't hear you well.
TH,
T, H.
YA,
Hmm?
YA.
Y, A. All right,
I'll take the tapered one.
wonderful. And
B-A-L-A-J-I.
B, A,
B, B,
B,
A,
A,
L-A,
A,
J-I.
J, I? Okay. So I guess Sean can get his microwave filters, right? Waveguide filters. S-H-Y-A-M? I'm working with you for almost a year now, I should know that spelling. All right.
Can I get filter implementation as
Hmm?
well?
Filter implementation as well?
Yeah,
And the spelling?
M-U-R-P-H-Y.
Murphy?
Yep.
Hmm. All done? Okay. I hope I can get that into my spreadsheet and send it to everyone.
Sounds interesting. How about just use the focus one?
That's one of the ones I was thinking, that's why I was looking at it. It doesn't.
Filters also.
I'm trying to coordinate some visiting lectures on different topics to get some of my faculty colleagues to help out with topics of their specialty. You know, it's good to see what other people are working on. Okay. Project A, reviews. So tentatively, I believe Monday we will have Dr. Montigny, and Friday we'll have, I believe, Dr. Jazzy. We will talk about different things, and we'll see if we can get some more of the faculty working in the microwave area. We'll tell you about their special areas of expertise. Now, if I make a mistake in any of these and I send you, just please send me your corrections. And don't get upset because I may not have a clear picture. So even the couple of pages that I printed, they're not here for the lecture today. Well, I wanted to talk about a few things that kind of fill in the gaps of things that we have talked about. The first one is the magnetron use in radar applications. People ask me about what is the magnetron used for, and I said, radar is one application. And even in microwave ovens, we still do something interesting to make this device work for different applications. You know that for radar you are sending pulses. And what we have seen is a magnetron that produces continuously sinusoids. So how do you get pulses out of those sinusoids? Also in the microwave oven, the way to reduce the power delivered to the food is by pulsing the signal rather than by turning it down. You can't turn it down. Well, I guess you can, but it's too complicated. So it's much easier to pulse a signal. And actually, if you're sending by a microwave and run it on a lower power, you would hear it on and off. You know? You can hear the signal itself or the humming of the microwave oven going on and off. And if you're defrosting something, for example, usually it's done at a very low heat. So basically, you are sending a pulse of microwave signal, and then you wait for a duration before you send another pulse. So the shape of the pulse eventually that you are sending is a sinusoid, and then off, and then another sinusoid, and then off, and so on and so forth. And that's basically also what you do for radar. You're sending a pulse of RF signal. So you're really modulating your RF, right, with a square pulse. That's your modulation. And the way to do that is basically, as you know, you have two fields running there. One is electric field, and the other one is magnetic field. Right? To pulse a magnetic field is kind of maybe too complicated, but pulsing the electric field may be easier. Right? So basically, you pulse your bias voltage up and down. Okay, so that's what you do. You can turn the filament off because that takes time until it cools down. You know, so turning the power off from the magnetron is basically done by biasing the high voltage, which is between the anode and the cathode. And by the way, you know, since the anode is the external component, usually the anode is the grounded one. So your voltage on the cathode is the high voltage here, and it's negative. Typically on most vacuum tubes, you're putting positive on the anode, and the cathode is the one that is grounded. That's a typical situation. Because of the magnetron construction, as you can see, the body here is really the cavity itself. So you make that the ground. And put the cathode at a negative high voltage. That's the situation that you do that. Now, if you're sending a pulse signal like this in a waveguide, what happens? All right, use a waveguide. We know that the waveguide has FC10, FC20, and by the way, many of you did an FC101 calculation, all right, without bothering to check on the FC20. You need to compare these to each other. These are the next two. You have to compare them and see which one is the lower. So people went to that and found it there and said, that's my bandwidth from 6.5 to 10 point something. And they forgot to check the FC20, all right? So it's important to check the FC20. Anyway, that's your bandwidth now of operation. Or you're sending a pulse. Now, a regular pulse like this will have a frequency spectrum that would extend way up in frequencies. You know that the step function, you have a U of t that goes with 1 over s, right? Isn't that what you get when you do a U of t in the Laplace transform, 1 over s? So it's 1 over f, kind of frequency spectrum. That's really what you get, the frequency spectrum, if you have a U of t. If you have a delta of t, this frequency spectrum of that is 1, and that goes uniform all over the frequency, all the way to infinity. So this is mostly baseband information, mostly baseband information. If you send this pulse here in this waveguide here, and that's your DC, and your waveguide only allows that much frequency component to propagate, obviously only a part of the spectrum is going to go through. Only a part of the spectrum is going to go through. But being modulated over RF, then it becomes a sideband fix. Then what you have now is the carrier, and this one is on top of that. So the frequency spectrum of this one here is basically the carrier here, and the sidebands, next to it. All right? And obviously that goes within your FC10 with the next cutoff, you are okay. So sending a pulse RF is not like sending a pulse, right? A pulse RF would contribute to the sidebands of the carrier, which is well within the bandwidth of the waveguide. So you shouldn't have an issue there. The reason I'm mentioning that is one of the questions that you have on the second midterm is related to pulse propagation waveguides. These are baseband pulses, these are not RF pulses. If you want to comment on both, that's fine, right? But RF pulses should be fine and should go through with no problem. The carrier would determine, if you are within the band or not. Okay? So that's just a good clarification, because you will see that exam problem when you open that exam. So that's one thing about that. The other thing is, here's your magnetron generating the megawatts, all right? Going up the tower to the antenna, sending these pulses, all right? And a reflection will come back. The order of magnitude of the reflection is very, very small, because that signal is going to propagate kilometers, for miles until it hits the target, and a weak signal. So this one here is very strong, and this one here is very weak. Will come back, and eventually it has to come down to a detector. So you have, so that's your source, and here's your detector. Detector is sitting here. All right, and eventually we need it to go to that. This is one link. There are no two lines here because you only have one antenna here. You're using the same antenna to send and receive. So what do we do here to make sure that we are okay? Because basically, if a small portion of the signal leaks into here, all right, it's going to overshadow your signal coming back from the reflection. In addition, it may be too strong to burn your detector. You try to increase the sensitivity of that detector a great deal to be able to detect these weak or very weak signals here. This is typically done, or that issue is typically done through what we call the circulator. The circulator device, the ideal circulator, has an S parameters of the phone, S of ideal circulator. Now, as you can see here is one port, 2 ports, 3 ports, usually it's a 4-port device. All right? So you would like it to be matched so you have 0 in the diagonal. Can't afford to lose any of your power by having a mismatch. You don't want any of that signal to bounce back and not be delivered. All right? Signal coming from 1, we want it to go to 2. So S21 should be 1. Right? That's an ideal situation. And shouldn't go anywhere else. All right? So we want it to be 0 here and 0 there. I'm sorry. Going vertically. S21. That's the signal from A1. This is signal coming from A1, signal coming from A2, signal from A3, signal from A4. And these are the B1, B2, B3, B4. Right? The columns are the A's and the rows are the B's. Signal coming from 2, you want it to be delivered to 3. Signal coming from 2, you want it to be delivered to 3. So you would like to see a 1 here. And we want it to be zeros everywhere else. Well, the concept of the circulator also says that the same concept should apply to the other ports as well. So you would also signal coming from 3, although I'm not going to be sending any signals from 3, but concept-wise, you need to see a 1 here, and also you need to see a 1 there. All right? And all the others are zeros. Although I'm not using them, but that's the concept of a circulator. Now, there are many designs for circulators. One simple one is basically like the same thing that we've done for the directional coupler. You have 2 guides with a couple of holes. And you would have these coupling coefficients here to be causing a phase shift, 90 degrees phase shift. So your signal coupling here would be 90 degrees phase shifted. And your signal coupling this way will be 90 degrees phase shifted. Meanwhile, you would introduce a phase shifter here in the media, 180 degree phase shift. That's right, phase shifter, phase shift. and those phase shift components can be designed to give different phases in different directions. So you get 180 degrees this way and 90 degrees this way. So what happens in this situation here is this signal here will arrive here with 180 degrees phase shift, but it also can go through this way, producing another 180 degrees phase shift. Right? The two packets here add, so your signal from 1 goes to 2 is no problem. The two components coming out are in phase with each other. Meanwhile, if you look at the signal here and the signal there, you will see this one goes 180 and 90, that's 270, and this one only goes through 90. So these two subtract. These two here add, and these two subtract. So play games with things like that, okay? That's a very quick and crude explanation to how a circulator works. But this is, this is what you want. There's so, like I said, there are several other possible designs for circulators, but they all are designed to make the signal from a port go to the next port, and that's the end of that. All right? So signal coming from 1 goes to 2, signal coming from 2 goes to 3, signal coming from 3 goes to 4, signal coming from 4 goes to 1. What we do is a fourth port here, obviously, if you have a 4-port device. 1, 2, 3, 4. Let's make it clockwise. 1, 2, 3, 4. All right? That signal goes this way, that goes this way, this goes this way, this goes this way. So here you put your source. Here you put your antenna. This one here you put your detector. And here you would just simply put a match. You load it with a match. So that port 4 is idle. So any signal going to 4 from 3, for example, would just be absorbed and dies away. Okay? One last thing that I was planning to cover today, and that's a couple of pages that I brought with me and I don't have them anymore, is related to the higher order modes in coaxial lines. We never discussed that after talking about cylindrical guides. I'll try to give you a recollection rather than exact. Any of you has the book? No one is studying the book today. No? Well, thank you. Get that equation from here. Coaxial line higher order modes 131, page 131 to 133. Okay, we did the cylindrical coordinate solution, and if you recall, we ended up with Second derivative with respect to rho squared plus 1 over rho partial rho of plus 1 over rho squared, second derivative with respect to phi squared, plus k of the cross section squared, all applied or equal.